Hello and welcome back to another episode of Measurement in a Minute. I'm your host, 𝗦𝗧𝗔𝗬 with Lakeside Process Controls. And in today's video, we're continuing our discussion around Rosemount micromotion flow meter technologies. In particular, we're talking about entrained air and ways to minimize it throughout your process, and as well as installation suggestions for your Coriolis flow meter. So how can we lower our Coriolis operating frequency? This is one of the first things we look at when trying to mitigate any sort of measurement errors in entrained air applications. And this is actually just by selecting the appropriate Coriolis flow meter. So different Coriolis flow meters operate at different frequencies, and we have this scale here to help us remember. But just think of this in terms of the shape of the tubes. So if we increase frequency and we go to something called our T series, which is a single straight tube design that's going to oscillate at the highest frequency. If we go all the way, up to our Elite series, you'll see that's operating at the lowest frequency. And if we review our equation for inverse Stokes number here, what we want to maximize is this number. Therefore, we want to reduce our frequency. Now, how does this make sense? I like to think about, playing with a ruler as a kid, where you would change the distances it was off your desk and hit it, and it would make higher or lower frequencies. Think of it the same way. When you have your ruler really close to the end of the table and you flick it, it has a really high pitch sound, and it has a really, really high frequency. The same kind of thing with the T series. It's that straight tube fixed at both ends, and you're trying to oscillate that. Versus the Elite series, it's fixed up at the top, but it's two tubes, and it's in this nice U shape that are free hanging. And those, when you hit those, if that was a ruler at the edge of your desk, that's going to be operating at a lower frequency. So just intuitively, that makes a bit of sense when you think about it. This actually has a very big impact on the measurement errors, and something that we want to look at in all of these applications. Now you might think, what a coincidence, your Elite series, your best Coriolis flow meter, has the best performance, but we can actually back this up with some pretty significant data. So if we look at this graph here, we're comparing low fluid viscosity, and I'll show you high fluid viscosity in a second. The x-axis is fluid velocity, the y-axis is gas void fraction, and the shaded area represents less than 1% error. So you can see by this that we can handle up to, say, maybe 5 or 6% gas void fraction with less than 1% error at the same fluid velocity as the F series. So F series, we kind of fall in the middle between the T and the Elite series. We don't even have the T series on here because the performance is so poor that we do not recommend it for these entrained air applications. Other applications, no problem. Entrained air applications, we see challenges. Now, when we go to high viscosity fluids, you can see an even greater impact. So you can see that we can measure less than 1% error with our Elite series, up to, say, maybe 12, 13% gas void fraction, and the F series maybe gets a little bit closer to 4 or 5%. Keeping every other variable the same, the only thing we're changing is frequency, and you can directly see the impact from these graphs here. So something to absolutely consider for your applications. Now, we can also do some things with our installation to mitigate these effects. So first of all, we actually recommend what we call the flag orientation for our Coriolis flow meters. As you can see here, this allows the bubbles to travel through and out and not get stuck. When we have tubes down or tubes up orientation, bubbles can get stuck in the Coriolis flow meter. This can have a whole bunch of other issues unrelated to just the fact that you're going to have measurement error from having bubbles in your flow. So that's what we absolutely want to avoid here. Another way we can reduce measurement errors is by also reducing bubble size. So that's the other part of that inverse Stokes number equation here. We can do this a few different ways. So first of all, we can increase the velocity of the fluid, increase the back pressure. That's going to push on those bubbles and make those smaller, reduce the decoupling effect, reduce our measurement errors. Also, if we're emptying vessels, right, and we're introducing bubbles that way, well, we can try not to. We can try to keep vessels at higher levels. Now, obviously, if part of your process is product transfer, you have to empty that. There's no way to avoid that, but we look at trying to mitigate that where possible. And then the last one, which is very important, is actually checking our pumps regularly, making sure we have adequate seals, because quite often that can pull in bubbles into our process unsuspectingly. So those are some other ways that we can, like I said, reduce that number on the bottom side of the equation there, that bubble size, and ultimately increase our inverse Stokes number, reducing our measurement errors. Should you have any questions about micromotion Coriolis flow meters or any other of our products, please reach out to us at www.lakesidecontrols.com. Thanks, have a great day.